Good morning, HOD Professor A.K. Chaturvedi sir, my seminar guide Dr. Sandeep Parashar sir, seminar coordinator D.P. Sharma sir, faculty members, examiners, and my batchmates. I am Komal pursuing my B.Tech from University Department of Mechanical Engineering, Rajasthan Technical University, Kota, Rajasthan. The topic of my seminar is self-aligning solar panels. First of all, I would like to give you an overview of why self-aligning solar panels. As we all know that the sun is a possible renewable resource for energy that is not being used at its full potential, mainly because present market solutions is not yet competitive with the fossil energy sources used today in terms of efficiency. However, the uses of solar panels is increasing, and therefore it is important that the solar panel efficiency increases as well. Improving the technology in the solar panel itself is one way to achieve this, but the surrounding equipment can be improved as well. By making the solar panel self-aligning, the energy from the direct beam of sunlight can be harnessed more efficiently. This presentation is structured as follows. Let's move on to the design implementation for self-aligning solar panel. The solar panel platform should have the following features. 2-axis rotation. That is, the platform needs to align itself with the sun to maximize the output. The first axle is the main axle for the direction of the support frame. The second axle is for the pitch angle that tilts the panel. Construction suitable for outdoor environment. This is the most important point we need to keep in mind while designing the solar platform. The platform has to be stable and robust to withstand stronger wind without external anchoring. Next is repositioning based on photoresistors value. The platform makes small incremental movements to best align with the sun when all resistors have the same value. Next, repositioning based on an output voltage from a solar panel. The platform rotates both axes to make a full scan of the celestial sphere, remembers where the highest output is, and then adjusts itself to that position. Startup. At first, we need to design a specific software program for the self-aligning solar panel platform. There are two different modes of measuring the optimal position. The program starts with making a full scan of the sky, reading the output voltage from the solar panel, and then aligns it to the direction with the highest output. This is the same approach as in mode 2. If the sun is clear and the values from the photoresistors are high enough to be accurate, the software will use mode 1. If it is cloudy or other sources of disturbances causes the photoresistors to have low values, it will not be possible to have accurate data from these for the aligning, and the self-aligning solar panel will continue with mode 2. The first and fastest mode will use 4 photoresistors and continuously compare their individual values. It will only make small incremental adjustments to the positioning of the solar panel. The 2 units on the sides A and B are used for the positioning of the main axis, and the 2 on the top and bottom C and D for the pitch axis to find the optimal position. The main axis will rotate to the direction of the unit A or B, with the highest value until the difference between A and B are inside a desired interval. The same procedure will follow for the pitch axis, but based on C and D. This will run as long as the values are high enough for reliable readings and fall back to mode 2. Now, what is mode 2? Mode 2. The second mode is a slower and a thorough method where the output voltage of a solar panel is measured while platform rotates on both axes and does a full scan of the sky. This is accomplished by rotating the axis in the following order until the pitch axis is 90 degrees. Main axis 360 degrees clockwise, pitch 18 degrees clockwise. Main 360 degrees counterclockwise, pitch 18 degrees clockwise. The self-aligning solar panel remembers the position with highest output and then aligns accordingly. It stays there for the set time interval and then evaluates if mode 1 is reliable in the same way as during the startup. Then the solar panel platform is based on multiple electrical components. These are combined in several ways to achieve the objectives. A block diagram of these components and how they are connected are shown in figure. First is Arduino. The Arduino Mega 2560 and Arduino Mega microcontroller is an open source microcontroller board with a strong community online. It is based on an ATmega 2560 microcontroller and has a series of both analog and digital input and output pins which can be controlled individually. Programming is easily achieved with the C language and transferred from a computer with a USB port. It is possible to power devices and sensors through the Arduino, which is powered from either USB or an external power source. The Mega model is chosen based on its increased number of input-output pins, 16 analog and 54 digital, and also that there is an extended 4K byte of permanent local storage of type electrically erasable programmable read-only memory available on the board. These properties are key characteristics for this project because the Arduino is the central unit. It manages the readings of all sensors, controls the motors based on the program logic, and also stores the data on its onboard memory. Next, photoresistors. The photoresistors will be used to read the current level of light in the surrounding environment. This project uses multiple photoresistors to reposition the platform by reading their individual values. Since the first positioning mode is solely relying on the photoresistors, it is important to achieve an accurate reading that is as accurate as possible. Therefore, it is of great importance to place these photoresistors at an optimum position. The self-aligning solar panels uses 4 units of photoresistors, one on each side of the solar panel, to determine the repositioning. This way it is possible to secure the correct direction. The top and bottom units give the input to the pitch axis and left and right gives input to the main axis. To align the self-aligning solar panel with the sun and optimize the output, the 2 rotational axes requires a way to power the rotating movements and trace where and when the axis will rotate. Servo motors has the ability to achieve this but lacks the accuracy needed. Stepper motors, however, have a greater accuracy and are therefore best suited for this type of project. Stepper motor. A stepper motor is basically a spinning magnet. There are numerous electromagnets around the central axle which is magnetized in a specific pattern of electrical pulses. This creates the mechanical movement that rotates the central axle. The motor can therefore move in steps when an electric pulse is received. By keeping track of the number of received input pulses, the stepper motor can be accurately controlled in an open loop, which means that no feedback information is necessary. There are 2 varieties of permanent magnet stepper motors, a unipolar stepper motor which have a complex winding design that do not require reversing the polarity of the electromagnets for the central axle to rotate. Therefore, no drive electronics is needed. The bipolar stepper motor has a simpler design as you can see in figure. However, it requires drive electronics like H-bridge control circuit to operate. These 2 stepper motors require drive electronics to function properly. Therefore, the self-aligning solar panel uses 2 L298N dual H-bridge motor controller, one for each stepper motor. This enables feeding the stepper motors with a higher current than the Arduino's digital pins can provide, which can only have an output of only 40 mm. The digital pins are still used as a control signal, but the main supply is from the Arduino's output pin. Next is solar panel. The self-aligning solar panel uses a monocrystalline solar panel. The solar panel is partly for demonstration purposes, but it also used as a measuring instrument during the second positioning mode. In this mode, the solar panel's output is continuously compared with the previous achieved peak output value until the entire celestial sphere is controlled. The highest achieved output from the solar panel is then stored for the self-aligning solar panel to reposition itself. Next is voltage divider. During the second positioning mode, the self-aligning solar panel requires to continuously measure the output from the solar panel to determine where the optimum placement is located. The output voltage from the solar panel reaches over 10 volts, and since the analog pins on the Arduino is only able to read up to 5 volts, a voltage divider is required to step down the voltage to readable level. The Arduino receives this step down voltage through an ADC which returns a value between 0 to 1023. The voltage is then calculated with the formula shown here, that is V output is equals to 5 by 1024 into V sensor. When the V output is this step down voltage and V sensor is the measured value from the sensor. The solar panel output voltage is then calculated through second formula, which is V input is equals to V output into R1 plus R2 upon R2, which is the general voltage divider formula, where R1 is equals to 2 kilo ohm and R2 is equals to 1 k ohm. There are the two resistors used to divide the voltage, and V input is the output solar panel voltage. With V input and the resistors provided, the circuit current and wattage can be determined through Ohm's law, and as well as the amount of wattage hours delivered by the solar panels. Next is circuit board. The voltage divider is put on a circuit board. On the same card are branches for connectors from the Arduino and also resistors for the photoresistors. Power supply. The battery used to supply the project with power is a lithium polymer battery with 3 cells. It has a voltage of 11.1 and the capacity of 2200 mAh. It is a battery used in many remote control vehicles. Next is hardware and mechanical design. The mechanical construction is presented here together with the different parts seen in the figure. Next is the part of mechanical design, support frame. The support frame is an assembled from 3 individual 2 mm thick water cut aluminium sheets, metal pieces. The engine mount on the stepper motor and clearance holes for the pitch axle and main axle have been drilled out. Pitch axle. The pitch axle is an aluminium rod with a 10 mm diameter that enables rotational movements around the pitch axis. The solar panel is attached to the pitch axle with 2 3D printed mountings. The pitch movement is enabled by a belt drive that is connected to a stepper motor. Next part is main axle. The main axle handles all the rotating movements. The axle is made in aluminium and is rated to fit a bearing house with 2 axial ball bearings. A similar construction as the pitch axle is applied on the main axle, where there is a belt drive that connects the main axle to the stepper motor. Next part is base plate. The base plate takes up the load from main axle, support frame, solar panel and pitch axle. A robustness requirement is needed, so unlike the other part, the base plate is water cut from a 3 mm steel plate. For support and stability, it has 4 30 mm legs of aluminium which hold up the construction. Next is plastic base plate. Underneath the steel base plate is a plate made of acrylic glass which is cut with laser. Its purpose is to hold the electronics in place and for fasten the cables. Now that was the hardware and mechanical part. Now move on to the results. So for the results, to obtain the results, we recorded the amount of seconds with sunlight per hour on the selected day for testing. It is shown in the figure. To stimulate a normal stationary construction, the self-aligning solar panel had its normal software turned off and ran a simple version of the program that only reads the voltage from the solar panel and calculates the wattage in the same way as with the other modes. The results are shown in the figure. To run the test for mode 2, the software was configured to bypass mode 1. The wait time between scan cycles were set to 15 minutes and the results are shown in the figure. To evaluate the difference between these setups, the data for the calculated watt hours are combined in the graph shown in figure. The stationary mode collected 2.14 watt hour while positioning mode collected 2.23 watt hour in the same amount of time. So what conclusions can be drawn from here? The testing shows that the results are positive in terms of generated electricity. We found that the self-aligning solar panel is more energy efficient as compared to the static solar panel. The efficiency is improved indeed. These are the references. If you have any question, I'm happy to answer them.
Yes. Why is monocrystalline solar panels used here? Why not polycrystalline?
Because monocrystalline solar panels are more efficient and have greater advantages than polycrystalline solar panels. As monocrystalline are space efficient, has long lifespan and are better in low light. Thank you.